Okay, so let's extend the discussion of beam stiffness matrix to approximate analysis of rectangular building frames. So as you see here, a typical building frame is like this. Okay, we have, for example, here we have 3 bays. Okay, and during earthquake, for example, we assume that the approximate sway of this structure is something like this, right? And this is true because we have rigid diaphragm. So we can consider this as rigid diaphragm brought by due to slab, because a slab has a large in-plane stiffness. So therefore, the displacement here, say this is delta 1, will be approximately the same here. I'm talking about the displacement of these nodes. Okay. Now it is now justified to code, no? to assign a code for degrees of freedom at this 1, 2, 3, 4 rooftop nodes as the same, like say 6. Okay, we can assign them a single degrees of freedom. So same goes with the second floor. So here we assume the lateral sway of the frame as code 1. So that kind of approximation, will drastically decrease the stiffness matrix of this whole structure, right? So imagine if we assume this as a 3D space having 6 degrees of freedom on each node. Okay, so again, if you consider this as 3D space frame, so imagine in general a 3D space frame has 6 degrees of freedom each node. So this will be 6. So how many joints here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 12 times 6, that will be about 72. So the global stiffness matrix will be 72 by 72. Okay. So since we have restraint here, that will reduce our S by how many? So we will less 1, 2, 3, 4, 24. So 72 minus 24, that will be 48 by 48. Okay. So in reality, if you have 3D building, that will be a large stiffness matrix. Now using our approximation by using a simple beam stiffness matrix, we can analyze a rectangular building frame like this. Okay. So again, we will assign a single degrees of freedom to this floor level and a single degrees of freedom also on this floor level. Okay, but the rotation, we have different code or degrees of freedom per rotation on this on each joint. Okay, so that will drastically decrease the stiffness matrix. Okay, and then so remember, this is the stiffness matrix, local stiffness matrix of our beam. Okay, and in if you will recall, we can transform the global force into local force. We can do that. But again, in our case, we will ignore the forces that will contribute the action. Okay, so because we will assume, again, as part of our approximation, that the building frame is inextensible. So therefore, On a typical concrete structure, let's say a low-rise building, axial deformation will is really not that much in a typical low-rise building. Okay, so that assumption again reduces the required stiffness matrix. So no axial deformation like in our original beam stiffness matrix, and just rotation. Right? Oops. Now, also, a typical building has either vertical or horizontal orientation. Vertical for column and horizontal for girder or beam. Now, in order to use the beam stiffness matrix for a vertical column, we need to transform the stiffness matrix. Okay, so that's why I want you to recall this transformation we had before, wherein we transform F to Q, the global to local Q. Now, instead of this arbitrary inclined member, we will now transform a vertical member. Now, this is, oops, okay. Yeah. Now, this is the vertical column. So, this is the local forces Q1 and Q2 as the moment, Q3 and Q4 as the moment. Now, let's transform that into global F1. So, F1 is also horizontal. And F2, moment F2 is the same orientation. Okay. And F3 is also horizontal. And as you notice, Q1, Q1 here is simply the opposite of F1. So, or they are numerically equal, negative sign. Uh, then how about Q2? Q2 is moment. Therefore, Q2 and F2 will be the same. Okay. How about Q3? Q3 here is going to the left because remember this is the original local member forces in our beam, right? Then when you twist it 90-degree, your Q3 will be like this one. Now this is our global F3. Okay, so that they are again numerically equal but opposite sign. Okay, and lastly Q4 is equal to F4. So they are both moment. Okay, having the same direction. Okay, because this is counterclockwise, counterclockwise, so counterclockwise, counterclockwise. So using this transformation, we can generalize the equation as in matrix form as the Q matrix is equal to T matrix times the F matrix. Remember, this is what we used before in our derivation of the global stiffness matrix. Now it turns out we have a diagonal matrix, but -1 is on the first element and on the third. And this now serves as your transformation matrix for column. Okay, so in order to transform the the local stiffness matrix of a beam, remember this is our local stiffness matrix of the beam, KL. Now, in order to get the global stiffness matrix of that for a column, And this is the formula we used before, T transpose K local times T, operating this transformation matrix, transpose this, multiply with K local, and then multiplying again with T, you will come up with this. Okay. So as you notice, it's still the same, but you will notice there will be a changes in sign. Okay. Here on 6L. Okay. What else? So here changes in sign. Okay. So that kind of transformation of the stiffness matrix of a beam to column will be used to approximate the analysis of a building frame. Okay, so in short, we will be able to get the rotation or the moment and the corresponding uh, reaction of the column. So this will be horizontal reaction as we did in the derivation. Now, as an example, let's try to analyze first a frame without sway. Okay, so it's a two-member frame. Okay, so although you have a lateral load applied going on this direction, we have a pin support here, so that will prevent the sway of this frame. So the deformation could be something like this, okay, something like that. Okay, so therefore we since this will rotate, this joint, okay? Oops, okay. And then again, we will also verify our solution using STAAD. So here's our SMAT for that. Okay, so I think we need to write down first here. Okay, so this is the free body of our two-member frame. So the code is 1234 because again it's a beam. Okay, now for member 2, for now let's code the vertical displacement as 5, and the rotation is of course to be consistent with the rotation on this joint. It will be coded as 4 also. Okay. By the way, I think this should be corrected. Yeah, okay. Might be something like this. Okay. Because we have a vertical load here. So let's set up K1. So K1, the codes are 1, 2, 3, 4. And I encircled only 4 because, again, we're assuming only a rotation on that joint. No vertical and horizontal displacement because this is a frame without sway. Okay. And again, as an assumption in a frame, an axial deformation is assumed negligible. Okay. Now for K2, since the ends here is only pin support, therefore you will have a rotation at 4 and a rotation at 7. Okay, so 5, 4, 6, 7. Okay, therefore, you have only two unknowns. So which is coded as 4 and 7. Okay, so our S matrix is 2 by 2. Now for our BU matrix, BU again is the location of the required DOFs, unknown displacements. So what's the location of 4 here? It's on the fourth, okay? Fourth, fourth element. And what's the location of 4 and 7 on K2? It's on the second and the fourth. That's why 2 and 4. Now, what will be the destination of this encircled code to our S matrix? So the 4 is located on the first here. So 1. And 4 and 7, 7 is located on the second. So that will be 1 and 2. Okay, 4, 7, 1, 2. Next is, since this is a frame with loaded along the span, so we need to get the fixed end forces again. So we have a lateral load on the column. On the assumption of fixed end forces, it's 24 kilonewton per meter. Our formula there is WL squared over 12 for the moment. Now, if you compute that, 24 times the length, which is, this is 10, right? While this one is 8. Okay, so 24 times 10 square over 12, the moment is 200. Okay, for the reaction, of course, 24 times 10 over 2 is 120. Okay, for the next member, we have a concentrated load on the midspan. So the formula is PL over 8. So 75 times 8 over 8 is simply 75. And for the vertical reaction, you just have to divide that by 2 since it's symmetrical. So this will be 37.5. Okay. Next is, so these QFs will be required to get the PF, P sub F. And what do we need? We only need the numbers or the values corresponding to our S, which is 4 and 7, right? So we need to add 4 values corresponding to 4, degrees of freedom 4. So negative 200 plus 75 is negative 125. And for code 7, you have negative 75. Okay. Remember, this is our formula. Okay. So I'll rewrite that here. As you notice, you don't have P vector, or because you don't have a load applied at the nodes. So this is 0. Therefore, this will be negative of negative 125. Negative 75 is equal to S times T. So S is determined using our SMAT code, and you can get D. Okay, so let's proceed to our SMAT. So this is the SMAT implementation of that. S matrix is again a null matrix, 2 by 2, because you have two unknowns. In elasticity is, I assume, 200 gigapascal, more like steel. And then input 10 and 8 as the length. I assume, since the problem is assuming a constant E, area, and I just assume an inertia of 300. Okay. I will show you later that since the problem is assumed as EI constant, uh, I want to show you that if I assume a different inertia, the answer will not be different that much. Okay, because again, although there's a given area here, because it's a frame without sway, wherein our assumption is there's no actual deformation and only rotation. Okay, there will be only rotation on this joint and on this joint. Okay, so inputting our BU and BB as we got earlier, and looping to 1 to 2 because we have only two members. Okay, now this is the transformation matrix that we got earlier for column. Remember, this is the transformation matrix. For horizontal beam, we need to of course do the same transformation matrix, but this is a diagonal matrix since um, there's no changes on our beam stiffness matrix because T transpose of diagonal matrix is still the same, right? So we come up with the same stiffness matrix, and looping again to 2 for our global stiffness matrix, incorporating the transformation matrix for each member. So this is our transformed global stiffness matrix. And again, as you notice, there's no changes on K2 and K nu sub 2 because uh, it's a horizontal member. But on K1 and K nu 1, the changes are on the sign, right? Okay, positive, negative. Okay, and same code for generating S. Now, as you notice here, our PF is positive 125 and 75. Because that's why I rewrite the formula here, because we have a negative here and negative on our elements. So that makes it positive. Okay, that's why I made this positive already. And that's it. Getting the inverse of this multiplied to P sub F, you have our displacement, both rotation. Now setting up the global displacements, because we have this, so we only have rotation here, right? So that will be, you don't have displacement on 1, rotation at 2, no sway at 3, but only rotation at 4. So that is D1. And for here, we don't have vertical displacements, so that is 0. And we only have rotation, so that's D1. And no vertical displacement, 0, and only rotation here, that will be D2. Okay, so what else? And again, this is the QF1, QF2, 1200, 200 we obtained here. And getting Q1, so using this formula, we will be able to get the local member forces. Q1, Q2 here. So I pasted this already here. This one. And this is our corresponding STAAD model. Okay, so analytical properties and supports. So we have fixed here and fixed pin here. Okay, and the loading is this one. We have a 24 kilonewton per meter lateral load and sorry, this should be, yeah, 75 kilonewton vertical load. Then where's post processing? Let's check the displacement. So exaggerate, press control. Okay, so as you see, there's really no sway. Therefore, our assumption that there's only rotation is valid. Okay. Okay, what's the rotation here? 0.011 and 0.018, very small. Okay. For node 3, yeah, very small. Okay, so let's check the reactions. Yeah, so 126 horizontal reaction and 18 kilonewton vertical reaction, which is the same here. Okay, so this is the remember, Q1 is all four sets for the column. Q1, this is Q2. Sorry. Uh, this one is the horizontal, 126.77. This one is the moment, 222. Okay. For Q2, this will be 18 is the vertical. Okay. So as a reaction, we only need this 126, 222, and 18, which is this one or this one. 126, 18. Okay. Where is the moment? 222. This one. Okay, 126, 222, and 18 vertical reaction. Okay. So that simple approximation using just beam stiffness matrix gives us an almost uh, accurate uh, answer, right? And if I want to see you, I want to show you that if I change the properties, something like this, okay, maybe I'll choose still one, change, yes, close, and then I'll assign this section here, assign, yes. So long as the inertia is constant as given in the problem, but I changed, so as you see, I changed the inertia, then analyze again, and of course the corresponding area. You will still don't mind this. Yeah. So as you see, we were also able to obtain almost the same answer: 126, 18, and 227 or 222. Okay, in terms of reaction, right? So 126, 222, and 18. Okay, because that's the assumption that on a simple frame, on a typical frame, you can assume a negligible axial deformation.